This is SpaceTime Series 24, Episode 15. Coming up on SpaceTime, NASA gives up on its Mars mole, an exoplanetary system with real rhythm, and SpaceX sets a new launch record. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA's finally given up on efforts to get its Mars mole working. The mole was part of the Mars InSight lander's heat flow and physical properties package developed by the German Aerospace Center DLR. The instrument included a 40-centimetre long spike attached by a tether embedded with temperature sensors to the lander. It was designed to draw some 3 metres down into the Martian crust, taking temperature readings along the way. By taking the red planet's internal temperature, scientists hope to better understand the internal heat engine driving Martian evolution and geology. However, while Martian managers have always described the mole as a drill, in reality it's actually simply a pile driver designed to hammer itself down into the soil. And it never really worked. Despite all sorts of efforts ever since its deployment 2 years ago, it only ever just bounced around, never really getting more than 2 or 3 centimetres below the surface. They even tried using InSight's delicate robotic arm to hammer the probe into the ground. That didn't work, and so they tried piling up additional soil around the probe in order to gain extra friction. But that proved useless as well. Eventually, after one final push with 500 additional hammer strikes but no progress, mission managers finally called it quits. Scientists claim the Martian soil's unexpected tendency to clump deprived the mole of the friction it needed to hammer itself down to a sufficient depth. The concept's design was based on soil mission managers had seen at other Mars sites, but it now seems that soil is very different from what the mole encountered. Oh well, you live and learn, I guess. This is SpaceTime. Still to come, an exoplanetary system with real rhythm, and SpaceX sets a new launch record. All that and more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, Namecheap.com. As their slogan says, search and buy domains from Namecheap at the lowest prices. Now, this is the service that our team at Bytes.com use to buy and manage our domain names, and we're really happy with the service support and value we're getting. Buying the right domain name shouldn't be hard, and with Namecheap, we've found it to be anything but that. And you can find your dream domain and join over 2 million happy customers when you register with Namecheap. Trusted with well over 10 million domains, you'll know you're in safe hands when it comes to turning your website idea into reality. And they've got some excellent tools to help you find the right name, like the handy search engine. All you do is type in your desired name, cross your fingers, and press search. And if what you want's already gone, and it does happen sometimes, they'll come up with some great alternative ideas. And if you're looking for some new inspiration, try the new website domain name finder, Beast Mode. It'll help you discover thousands of domain names fast. We've found their prices to be excellent, management tools intuitive, and they're easy to use with excellent custom support if you need it. All in all, it's a great experience all round if you're looking to pick up a domain name or two. So why not check them out and help support our show at the same time? Just visit spacetimewithstuartgary.com/Namecheap. That's spacetimewithstuartgary.com/Namecheap, and Namecheap is one word. You'll find the URL details in the show notes and on our website. Just visit the support page. That's spacetimewithstuartgary.com/Namecheap. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Astronomers have discovered an unusual star system containing 6 exoplanets, which are locked in orbits that act more like a rhythmic gravitational dance. The system, called TOI 178, is located some 205 light-years away in the direction of the constellation Sculptor. The planets in the system are orbiting an orange spectral type K dwarf star, a little less massive and slightly cooler than the Sun. Astronomers originally thought they spotted two planets going around the host star in the same orbit, and that would have been strange enough. But the study's author Adrian Lelou from the University of Bern says more detailed observations revealed something entirely different. It wasn't two planets orbiting the star, roughly the same distance from it, but rather multiple planets in a very special configuration. The findings, reported in the journal Astronomy and Astrophysics, revealed that the system boasts at least 6 planets and that all but the closest to the star are locked in a rhythmic dance as they move around in their orbits. In other words, they're in what astronomers call resonance. This means they're in orbital periods which repeat themselves as the planets go round the star, with some planets aligning every few orbits. A similar resonance is observed in the orbits of 3 of Jupiter's moons, Io, Europa and Ganymede. Io, the closest of the 3 to Jupiter, completes 4 full orbits around Jupiter for every single orbit that Ganymede, the furthest away, completes, and 2 full orbits for every single orbit Europa makes. But the 5 outer planets in the TOI 178 system follow a much more complex chain of resonance. While the 3 Jovian moons are in a 4-2-1 resonance, the 5 outer planets in the TOI 178 system follow an 18-9-6-4-3 chain. So, as the second planet from the star and the first in the resonance chain completes 18 orbits, the third planet from the star and the second in the chain completes 9 orbits, and so on. In fact, the authors initially only found 5 planets in the system. But by following this resonant rhythm, they calculated where in its orbit an additional planet would be. And when they had the next window to observe the system, there it was. This dance of resonant planets also provides clues about the system's past. Because the orbits in this system are so well ordered, it suggests that this system's evolved quite gently since its birth. Now, if the system had suffered a significant disturbance, such as a major impact event, the fragile configuration of orbits would not have survived. But when you look at the characteristics of the planets in the system, this brings up its own confusion. You see, the exoplanets in the system include a terrestrial world very similar in density to the Earth. And right next to it is a very fluffy planet with just half the density of Neptune, and that's followed by another planet which has about the same density as Neptune. So this is all very different from our own solar system, where the planets are sort of neatly arranged with the rocky, denser planets close to the central star, and the fluffy, lower density planets, the gas giants in other words, further out. Lelou says the contrast between the rhythmic harmony of the orbital motion and the disorderly densities of the planets themselves challenges science's understanding of the formation and evolution of planetary systems. The authors studied the system's unusual architecture using data from the European Space Agency's CHEOPS spacecraft, together with ground-based observations from the Very Large Telescope, the Next Generation Transit Survey Instrument, and the Speculus Telescope Array, all of which are part of the European Southern Observatory's Paranel Observatory site in Chile. The 6 planets have sizes ranging from about 1 to 3 times the size of the Earth, with their masses varying from 1.5 to 30 Earth masses. Some of the planets are rocky but larger than the Earth. These planets are known as super-Earths. Others are gas planets, like the outer planets in our solar system, but they're much smaller, and these have been called mini-Neptunes. Although none of these 6 exoplanets orbits their host star in the habitable zone, the authors suggest that by continuing the resonance chain, they may well find additional planets that could exist in or very close to this zone. To find out more, Andrew Dunkley speaking with astronomer Professor Fred Watson.
Let's talk about these exoplanets that have been discovered. What's so unusual about them, Fred?
They were a puzzle, actually, from the word go. But the unusual thing, and I'll say it now, but we'll talk about it in detail, is the resonances between these planets, where one planet orbits in an integral number of orbits of the other planet, if I can put it that way. The story, though, goes back quite a long way. This is an object that's been observed for quite a long time. The star is called TOI 178, and TOI is target of interest, which I think is a Kepler designation from the Kepler spacecraft. This object is about 200 light years away. So what we've got here is a star that has revealed the presence of planets by the fact that the light of the star dims as the planets pass in front of it or transit. And originally, astronomers thought that what they were seeing were 2 planets which actually were in the same orbit. In other words, one following the other around. But then a closer analysis shows that actually it's not two planets orbiting the star at the same distance, but a lot of planets, and in fact there are 6 now that are known, which are performing this kind of resonant dance where the orbits are interconnected. This work, I should say, has come from the Université de Genève in Switzerland and the University of Bern. Both have strong astronomy groups, actually, both of them. So, okay, what's the situation? Well, you can look at it in terms of what's happening in our own solar system. There are many resonances in our solar system. The best known is 3 of Jupiter's moons, Io, Europa and Ganymede, which have this 4:2:1 ratio in the time that it takes them to go round. So Europa goes round twice in 4 orbits of Io, and Ganymede goes round once in 4 orbits of Io, and that means it goes round once in 2 orbits of Europa. So it's a 4:2:1 resonance. The other good well-known one is Pluto, which is in a resonant orbit with Neptune. So Pluto goes round twice for every 3 orbits of Neptune. What's happened is that as these things have orbited over billions of years since the formation of the solar system, the gravitational forces have conspired to pull them into this sort of orbital resonance situation. What's happened now, though, is TOI 178 has been carefully observed. So it too has a resonant chain, as it's called. You call it a resonance chain. And it's 18:9:6:4:3. That's the ratio of 5 of the 6 planets. So let me just read the story. While the second planet from the star completes 18 orbits, the third completes 9 orbits, the fourth completes 6 orbits, the fifth completes 4 orbits, and the sixth completes 3 orbits. That's the 18:9:6:4:3 resonance chain. The innermost one actually doesn't follow that mathematical curiosity, I guess you might call it. But the reason why this is valuable is it sort of tells you about the way these planets have evolved, how the system has evolved since the birth of the star. And it suggests that the evolution has been what one of the astronomers describes as gentle. This is Jan Alibert from the University of Bern. He says the orbits in this, I think it's a he. The orbits in this system are very well ordered, which tells us that this system has evolved quite gently since its birth, rather than, and as they go on to say, for example, by a giant impact stirring things up. It's a configuration that wouldn't have survived that. But there is one peculiarity about it, Andrew, and that is these stars are all very different. In fact, Nathan Hara, another, I think I remember working with him years ago, again at the Université de Genève, he says that even if the arrangement of the orbits is neat and well ordered, the densities of the planets are much more disorderly. So there's a really nice quote again from one of the astronomers. This contrast between the rhythmic harmony of the orbital motion and the disorderly densities certainly challenges our understanding of the formation and evolution of planetary systems. Because if they've had this kind of gentle evolution, you'd expect it would have turned out like it is in the solar system, with one type of planets in the inner part of that solar system and the other type well out. But no, they're all mixed up. And I might just mention, since I'm always glad to get a plug-in for this organisation, several telescopes were involved with this work, but in particular the very large telescope of the European Southern Observatory, ESO, with which Australia has a 10-year strategic partnership. So ESO is very close to our mind here in the world of astronomy in Australia.
As you mentioned, we can learn a lot from this discovery. What I wonder about is, we take for granted that the rocky planets are close into the sun and the gas planets are out wider, but there have been exoplanets discovered where there are huge gas giants very close to their parent star. So we are not, I suppose, typical. Or
no, that's right.
Have they discovered that is more typical than other scenarios, or it could just be anything?
One of the reasons why, and the things you're talking about, the gas giants right next to their stars, they're called hot Jupiters. And we've found a lot of those. And one reason for that is probably that they're the easiest to find. of all the planets going around other stars, they're actually the easiest ones. The signal, the information that they present is very much the information that's most readily detected. But you're also right that there are things about our solar system that we don't understand. And there's all the people who look at the history of orbits in the solar system, and you can do that by running the clock backwards, suggest that the gas giants in particular have moved around quite a lot, migrating inwards and outwards in the solar system, probably not within the central zone where the rocky planets are, but certainly in and out. And in fact, one piece of research suggests that maybe Neptune and Uranus actually reversed position at some point. These are really interesting features of our solar system. But still, the scientists who work on this kind of thing will learn a lot from the famous exoplanet system TOI 178, which I think has still got many secrets to reveal.
That's Dr. Fred Watson, an astronomer with the Department of Science, speaking with Andrew Dunkley on our sister program, Space Nuts. And this is SpaceTime. Still to come, SpaceX sets a new launch record, and Orion the Hunter dominates the night skies on February Skywatch. All that and more coming up on SpaceTime. SpaceX has set a new record, launching 143 satellites on a single rocket. The mission payload included 133 commercial and government spacecraft, as well as 10 SpaceX satellites. The flight aboard a Falcon 9 rocket from Space Launch Complex 40 at the Cape Canaveral Space Force Station in Florida had been delayed by a day because of bad weather.
And the vehicle is in startup. Both stages are beginning to pressurize for launch. In a few seconds here, we should be hearing the launch director give the final go for liftoff.
LD on countdown 1, go for launch.
And there you heard it. That is the final go for launch. All systems are go for the Transporter-1 mission from Cape Canaveral Space Force Station in Florida.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
Impulse pitching downrange. Stage 1 chamber pressure is nominal.
We are T plus 43 seconds into flight. Falcon 9 has cleared the tower and is currently throttling down to prepare for max Q at around the T plus 1 minute and 12 second mark. Max Q is where the vehicle will experience the highest amount of aerodynamic pressures.
Falcon 9 is supersonic, max Q.
And we've just passed max Q. All is looking good with the stage 1 trajectory. In about a minute, we have 3 events coming up in quick succession. First up is main engine cutoff. That's where the 9 engines on the first stage will shut off, followed by stage separation, where the first and second stages will separate from one another. Shortly after that, we'll have second engine start 1. The Merlin vacuum engine on the second stage will ignite its engine and continue its journey into orbit.
MVAC engine chill has begun. Main engine cutoff. Stage separation confirmed.
Coming up in a few seconds, we should have the fairing deploy.
MVAC ignition. Fairing separation confirmed.
The 2 fairing halves have separated and fallen away from the vehicle, exposing the 143 spacecraft to the vacuum of space. And as a reminder, our recovery vessel, Namecheap, will be attempting to recover the fairing halves today from the water. The second stage, specifically the MVAC engine, it's currently in the first of its 2 MVAC burns. This burn should last for about another 5 minutes or so. The next milestone for the first stage will be its re-entry burn. Falcon 9 needs to execute an entry burn to slow itself down before hitting the dense parts of the atmosphere. Without this burn, relying on the atmosphere alone to slow Falcon 9 down will put unnecessary strain on the rocket. And that entry burn is coming up at around the T plus 7 minute and 47, just a few minutes from now. This is the Transporter-1 mission for SpaceX, the first dedicated small-sat rideshare program mission, and it's also the 3rd mission of 2021. We're just waiting on the next major event for this mission, which is the first stage entry burn, the periodic bursts of gas from the first stage. That is nitrogen from our attitude control systems. They help to orient the first stage as it continues to make its descent back towards Earth. Hypersonic grid fins, and those help to steer the first stage back as it returns back to Earth. As for the second stage, MVAC performance looks nominal. Just a few seconds after we finish the stage 1 entry burn, we'll be shutting off the second stage Merlin vacuum engine and enter a small coast phase. Again, we'll need to relight this engine later on in the mission to get to our eventual destination in orbit.
Stage 1 FTS is safe.
We are about 45 seconds away from that stage 1 entry burn. For the entry burn, it is a 3-engine burn, so 3 of the 9 Merlin engines on the first stage will relight and start to slow the stage down before it hits the denser parts of the Earth's atmosphere.
Stage 1 entry burn startup.
And there's the entry burn. 3 of the 9 Merlin engines have relit. This burn is expected to last for about 30 seconds.
Second stage and terminal guidance.
Stage 1 entry burn shutdown.
The entry burn has concluded, and in just a few seconds, we should be hearing the call out for second engine cutoff, but we'll shut down the second stage MVAC engine.
FDS is saved.
Also signal stage 1, Cape expected.
The second stage has shut down its engine. Now, as I mentioned earlier, we are going to be attempting to recover the booster for a 5th time.
Nominal parking orbit insertion.
On our drone ship, Of Course I Still Love You. The first stage has one more burn left, the landing burn, and it begins just before we touch down and provides the booster with a soft descent before we land. That should be starting up anytime now. And we did get confirmation of the second stage that it did reach a good parking orbit.
Stage 1 landing leg deploy.
LOS stage 2, Cape Canaveral expected.
And Falcon 9 returns safely once again. That is the 5th time for this particular booster and the 73rd recovery of an orbital class rocket.
This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for February on Skywatch. February is the second month of the year in the Julian and Gregorian calendars. It's also the shortest month of the year, and the only one which is a length less than 30 days. The month is 28 days in common years and 29 in leap years, with a quadrennial 29th day being called a leap day. This additional day every 4th year is needed to keep the calendar year synchronized with the astronomical year. Because seasons and astronomical events don't repeat in whole numbers of days, calendars that have the same number of days in each year tend to drift over time with respect to the event the year is supposed to track. By inserting an additional day every 4th year, this drift can be corrected. The extra days occur in years which are multiples of 4, with the exception of years divisible by 100, but not by 400. Similarly, in the lunisolar Hebrew calendar Adar Aleph, a 13th month is added 7 times every 19 years to the 12 lunar months in its common years, in order to keep its calendar from also drifting through the seasons. And in the Baha'i calendar, a leap day is added whenever it's needed in order to ensure that the following year begins on the vernal equinox. The length of a day is also occasionally changed by the insertion of leap seconds into Coordinated Universal Time, or UTC, more often referred to as GMT or Greenwich Mean Time. This is needed because of the variability in Earth's rotational period. But unlike leap days, leap seconds aren't introduced on a regular schedule, since the variability in the length of the day is not entirely predictable. Okay, let's turn our attention to the sky now. And throughout most of February, sky watchers in the southern hemisphere may be lucky enough to catch sight of the occasional meteor associated with the Alpha and Beta Centaurids meteor showers. Now, as their names suggest, they appear to radiate out from the direction of the constellation Centaurus as 2 separate streams, although they rarely produce more than 1 or 2 meteors per hour. They usually peak around February the 8th, and to see them at their best, you really should be looking towards the east a few hours before dawn. Okay, looking north now, and high in the sky is the famous constellation of Orion the Hunter. Orion is one of the best known and most recognized constellations in the sky. In Greek mythology, Orion was the son of a Gorgon and Poseidon, who was also known as Neptune, the god of the sea in Roman mythology. Orion was a mighty but egotistical and conceited hunter, who once boasted that his skill would allow him to kill all the world's animals. So the earth goddess Gaia sent Scorpius the scorpion to kill him and save the animals. Orion was stung in the shoulder, but then the healer Ophiuchus intervened to save him and crush the scorpion. Both Orion and the scorpion were then placed in the heavens to play out the story each year, with Scorpius rising in the east as the defeated Orion sets in the west. Now, a variation of this fable speaks of Orion getting a little bit too close to Artemis, the goddess of chastity. Now, her brother Apollo didn't approve of this relationship and tricked Artemis into testing her skill by shooting an arrow at a distant speck on the ocean. What Artemis didn't know was that that speck was actually Orion, swimming to escape the giant scorpion created to kill him. When Artemis discovered what she had done, she placed Orion's body in the sky as the stars we see today. Similar variations to this story appear in other cultures, including ancient Egypt, where Orion is known as Osiris, the god of the underworld and of regeneration. The very earliest depiction that's been linked to the constellation Orion is a prehistoric mammoth ivory carving found in a cave in the Arch Valley in West Germany in 1979. Archaeologists have estimated that it would have been fashioned somewhere between 32,000 and 38,000 years ago. The distinctive pattern of Orion has been recognized in numerous cultures around the world, including ancient Babylonian star catalogues dating back to the Late Bronze Age. Orion's easily identified by its rectangle of 4 stars, surrounding a central trio of stars in a row which form Orion's belt. And hanging from the belt are the stars which make up the Sword of Orion. To those of our listeners in the southern hemisphere, Orion appears to be upside down, with the sword on his belt pointing upwards. And if you look really, really carefully, you'll notice that the middle star in the sword looks a bit fuzzy. That's because it's not a star, but rather a huge star-forming region known as Messier 42 or M42, the Great Nebula in Orion. Located some 1,344 light-years away, M42 is the nearest large star-forming region to Earth, containing hundreds of newly forming stars and protostars. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. The Orion Nebula is more than 24 light-years across, and it contains as much mass as 2,000 suns. It's one of the most scrutinised and photographed objects in the night sky, and is among the most intensely studied celestial features. The Orion Nebula has revealed much about the process of how stars and planetary systems are formed from collapsing molecular gas and dust clouds. By studying M42, astronomers have directly observed protoplanetary disks, brown dwarfs, intense and turbulent motions of gas, and the photoionizing effects of nearby massive stars in the nebula. The Orion Nebula contains a very young open cluster known as trapezium due to the asterism of its 4 primary stars. The trapezium itself is a component of the much larger Orion Nebula cluster, an association of around 2,800 stars within a diameter of just 20 light-years. The brightest star in the constellation of Orion is the semi-regular variable red supergiant Betelgeuse, which represents the scorpion's sting on Orion's shoulder. Currently known as Betelgeuse, and commonly referred to by the public as Betelgeuse, don't say it 3 times, the names are both tortured mispronunciations of the original Arabic name Ibtal Yauza, meaning the hand of the big man being Orion the Hunter. Located some 643 light-years away, Betelgeuse is the 9th brightest star in the night sky. And it's big, really big. In fact, red giants like Betelgeuse are among the largest stars in the universe, at least in terms of volume, although they're by no means the most massive or luminous. Calculations of Betelgeuse's mass range from slightly under 10 to a little over 20 times that of the Sun, and it shines with some 100,000 times the Sun's brightness. If it were placed at the location of our Sun at the centre of our solar system, its visible surface would extend almost as far out as Jupiter, engulfing the orbits of the planets Mercury, Venus, Earth and Mars, as well as the main asteroid belt. Betelgeuse began its life around 10 million years ago as a spectral type O or B blue star. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in. Then there are spectral type K orange stars, and the coolest and least massive stars are spectral type M red stars, often referred to as red dwarfs. Each spectral classification system is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 being the coolest, and then a Roman numerals added to represent luminosity. Put them all together, and our Sun is officially classified as a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are between 75 and 80 times the mass of Jupiter, or about 0.08 solar masses. Red supergiants are fascinating objects. After spending billions of years fusing hydrogen into helium in their core, a star's core hydrogen supply eventually runs out, and the balancing act between nuclear fusion pushing outwards and gravity pushing inwards stops, with gravity winning. The entire mass of the star then comes crashing down onto the core. This causes a dramatic increase in the core's pressure and consequently temperature. Things get hot enough to trigger what's called a helium flash. This causes the core helium, which has been created in the star, to begin fusing into carbon and oxygen. At the same time, the hydrogen-rich region around the stellar core has now moved down into that region where the temperatures and pressures are high enough for hydrogen fusion into helium to commence in a shell around the core. Now, as all this is going on, the increasing core temperature results in an increasing level of luminosity, and the resulting radiation pressure from the shell burning causes the outer diffuse gaseous envelope of the star to expand to hundreds of times its previous radius. And as the now bloated star's chromosphere or visible surface moves further away from its core, it cools down, turning redder. Hence the star has become a red giant. Small stars like the Sun eventually lose their outer envelopes completely, which continue expanding outwards as planetary nebula. This ultimately exposes the star's white-hot stellar core as a white dwarf, which is then left to slowly cool down over the eons of time. However, stars with masses more than around 8 times that of the Sun experience a very different fate. Unlike the Sun, their fusion cycle doesn't end with helium in the core fusing into carbon and oxygen. They have enough mass to fuse carbon and oxygen in their core into progressively heavier and heavier elements through a different process, while the shell burning around the core also fuses progressively heavier and heavier elements: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, nickel, and eventually iron. These stars have become supergiants. Eventually they'll explode as core collapse supernovae, ending up as either super-dense strange objects called neutron stars, or even stranger objects called black holes, singularities of infinite density and zero volume, where the laws of physics as science understands them no longer apply. It's too early to tell whether Betelgeuse's ultimate fate will be as a neutron star or black hole. As a red supergiant, Betelgeuse is reaching the end of its life, and it's expected to explode as a core collapse or Type II supernova any day now. Of course, in astronomical terms, any day now could mean tomorrow, or it could mean 1 million years from now. When it does explode, Betelgeuse will temporarily outshine all the other stars in our galaxy, and it will be clearly visible in the daytime sky on Earth. The last star to be seen by humans to go supernova in our galaxy was Tycho's star. That was in 1572, and that was before the invention of the telescope. Diagonally opposite Betelgeuse, marking Orion's left foot, is the blue supergiant star Rigel, the second brightest star in the constellation Orion. Rigel is part of a triple or possibly quadruple star system with 3 or 4 small companion stars. The primary star, Rigel A, is located some 863 light-years away and has about 23 times the mass of the Sun. The star's already exhausted its core hydrogen supply, and it's swollen out to between 79 and 115 times the Sun's radius, and is somewhere between 120,000 and 279,000 times as luminous. Like Betelgeuse, it's now fusing progressively heavier and heavier elements in its core, meaning it too will soon go supernova. Rigel A pulsates quasi-periodically and is classified as an Alpha Cygni variable star. Alpha Cygni variables are variable blue or white supergiant stars which exhibit non-radial pulsations, meaning some areas of the star's surface are contracting while others are expanding. This causes irregular variations in brightness due to beating of multiple pulsation periods. The pulsations are likely caused by iron opacity variations and typically have periods ranging from several days to a few weeks. Rigelet's companion star Rigel B is some 500 times fainter than the supergiant, and it's only visible with a telescope. Rigel B itself is a spectroscopic binary system comprising two main sequence blue-white stars. Main sequence stars are those happily fusing hydrogen into helium in their core. And spectroscopic binaries are double-star systems orbiting each other so closely and at such an angle that they can only be visually separated, at least from our viewpoint on Earth, by their spectroscopic signatures. The two stars making up Rigel B are estimated to be 3.9 and 2.9 times the mass of the Sun, respectively. And one of those stars, Rigel BB, itself may be a binary. It appears to have a very close visual companion, Rigel C, of almost identical appearance. The third brightest star in Orion is Betelgeuse, Orion's left shoulder. It's a spectral type B main sequence blue star, with about 8.6 times the mass and 6 times the radius of the Sun. Betelgeuse is located about 250 light-years away. It has an estimated age of approximately 25 million years. Now that's old enough for a star of this mass to have consumed much of the hydrogen in its core and begin the process of evolving away off the main sequence into a blue giant. One of the most stunning nebula in Orion is the spectacular Horsehead Nebula, Barnard 33. The Horsehead is a dark nebula located just south of the star Alnitak, which is the furthest east on Orion's belt, and is part of the much larger Orion Molecular Cloud Complex. Located around 1,500 light-years away, the Horsehead Nebula was first recorded in 1888. It's one of the most identifiable nebulae simply because of the shape of its swirling clouds of dark dust and gas, which really does bear an incredible resemblance to a horse's head. To the west of Orion's belt, you'll see a V-shaped grouping of stars which represent the head of Taurus the bull, who in Greek mythology was changed by the god Zeus to carry Princess Europa off to Crete. The V is also part of a large open star cluster known as the Hyades. One of Taurus's eyes is the giant orange star called Aldebaran, or the Follower, which is located around 65 light-years away and has about 1.5 times the mass of the Sun. Aldebaran is thought to contain a number of Jupiter-sized planets. Aldebaran's already evolved off the main sequence, having exhausted its core hydrogen fuel supply. It follows the Pleiades, or Seven Sisters, a spectacular open star cluster to the northwest of the V. Located in the constellation Taurus, the Pleiades is one of the nearest and youngest open star clusters to Earth, located just 443 light-years away. There's a story in Greek mythology which tells us that Orion fell in love with the Seven Sisters and pursued them for a long time. Eventually, Zeus turned both Orion and the Pleiades into stars. Interestingly, a similar story is told in the Aboriginal Dreamtime culture of the Great Victoria Desert region near Aldea in outback South Australia. Orion's described as a young male hunter who chases but never catches the Pleiades, who are a group of 7 young women. In Orion's right hand is a club filled with magic fire and represented by the red giant star Betelgeuse. However, the Pleiades' older sister, represented by the Hyades star cluster, taunts Orion, standing in front of him. She defensively lifts her foot, which is the star Aldebaran, and is also full of fire magic. And this causes Orion great humiliation, putting out his fire and allowing the Seven Sisters to escape. Now, one of the interesting facts about this ancient Dreamtime story is that it accurately describes the variability of Betelgeuse, which brightens and fades over a 400-day period. The Pleiades' Seven Sisters story is remarkably similar to legends found in many other cultures around the world, and which haven't had any contact with each other for tens of thousands of years. The Pleiades' 7 brightest stars can be seen with the unaided eye, hence the Seven Sisters nickname. But this spectacular open star cluster actually consists of more than 100 stars. Now, if you follow Orion's belt to the east, it brings you to Sirius, one of the nearest and brightest stars in the sky. Located just 8.7 light-years away, Sirius is a binary star system with a spectral type A white star orbited by a white dwarf. It's the brightest star in the constellation Canis Major, the Great Dog. In Greek mythology, Sirius was the dog star and the canine companion of Orion the Hunter. To the ancient Egyptians, Sirius was known as the god Anubis, lord of the underworld, who had the head of a dog and who invented embalming, the funeral rites, and who guided one through the underworld to judgment, where he attended the scales during the weighing of the heart to determine one's fate in the afterlife. Later, Anubis was replaced by Osiris as lord of the underworld. Sirius also represented the god Isis, and ancient Egyptians initially based their calendar on the star's yearly motion across the sky. Now, if you look high in the southern sky in February, you'll see the star Canopus, a white supergiant located 313 light-years away, the second brightest star in the night sky after Sirius. In Greek mythology, Canopus was the helmsman of the Greek king Menelaus, and the brightest star in the constellation Carina, which represents the keel of the boat used by Jason and the Argonauts in their quest for the Golden Fleece. Located nearby are the vessel's sails, represented by the constellation Vela, and the roof of the boat's rear cabin or poop deck, which is represented by the constellation Puppis. Also in the southern skies this time of year, you'll see the large and small Magellanic Clouds, which are two dwarf galaxies orbiting our own galaxy, the Milky Way. The Magellanic Clouds were known to the Polynesians and Maori, and served as important navigation markers. They're named in honour of the Portuguese navigator Ferdinand Magellan, who was the first European to sight them during the first circumnavigation of the Earth between 1519 and 1522. Magellan himself didn't complete the circumnavigation. He was killed in the Philippines during the Battle of Mactan. Right now, the Large Magellanic Cloud is located almost directly overhead and is about 163,000 light-years away. Although it looks like an irregular dwarf galaxy, astronomers have classified it as a disrupted barred spiral. It's around 14,000 light-years in diameter and contains about 10 billion times the mass of the Sun. Located slightly lower and to the west, you'll see the Small Magellanic Cloud, which is located around 200,000 light-years away. It's classified as an irregular dwarf galaxy, about 7,000 light-years wide, with about 7 billion times the mass of the Sun. Astronomers speculate that it too was once a barred spiral galaxy, but had become disrupted by the gravitational tidal perturbations of the Milky Way. Jonathan Nally, the editor of Australian Sky and Telescope magazine, joins us now for the rest of our tour through the February night skies.
G'day, Stuart. Well, for us in the Southern Hemisphere, we've got summer sort of on its last legs, I suppose, or the last third at least. So our summer formally in a place like Australia is December, January, February. So in February, we're on our last third of summer. So
the rest of the world thinks we're all really stupid doing that.
I know. They think, why do you do it that way?
Yeah, everyone else, is it everyone else who does it from summer solstice to...
Not everyone. Not everyone. No, not everyone. No, not everyone. And certainly people who live on the equator couldn't give a toss.
Yes, wet season, dry season. That's it.
They're precisely right. Yeah, for every place. I mean, our seasons really are artificial. They really should be based on each local place, but of course that would be difficult to do. Yeah, the other people do it according to the equinoxes and the solstices and things, but there's arguments to and fro.
It's to do with the amount of heat the oceans retain over the season.
You get a time lag. Yeah, that's right. Yeah.
But as you were saying,
so as I was saying, we're in the last bit of summer, last third or so of summer. Still have lots of great stargazing weather. We've got warm nights, you've got clear skies, lots of great constellations and things to see and do. We're fortunate in the Southern Hemisphere that the sort of constellations that are around in our summertime are some of the best ones. So for our friends up in the Northern Hemisphere, these best constellations are in the middle of their winter when it's freezing cold outside and you don't want to go outside at night and have a look at the stars. So we're a bit lucky that way. So let's have a look at some of the things we can see. Let's start with the Milky Way, which is the faint band of light which at this time of the year stretches across the whole sky from south to north. The Milky Way is just our galaxy seen from the inside, okay? If we could look at our galaxy from the outside, it would look like one of those typical spiral galaxy photos, right? So a spiral galaxy, if you look at it from the top or the bottom of this big round thing with spiral arms or whatever, if you look at it from the side, it's very thin, it's edge on. Very, very thin. So it's like a discus, if you like.
Although ours is slightly warped at the edges.
Speak for yourself. So it's like a discus, and we're inside one of the spiral arms. So when we look out into the night sky, we're looking at the sky around us inside the flat disk. So that's what the Milky Way is. It's just a milky appearance of millions and millions of stars that are too sort of dim and sort of all merged together. But you can pick out, of course, lots of individual stars, and they're the ones that we have made up into constellations via sort of join the dot affairs. So let's go along the Milky Way, look at the constellations and the bright stars and what we can see. So we'll start right down the south. We've got the Southern Cross. Two of the stars in the Southern Cross are actually in the list of the top 25 brightest stars in the night sky. And one of the third star in the Southern Cross is number 26. Southern Cross is the smallest constellation in the night sky. A lot of people, when they first see it, think, oh, it's pretty ordinary, but I think it's fantastic. It's this beautiful, compact little crucifix group of stars.
So easy to find.
Yeah, really easy to find. And with three of them being so bright, you really can't miss it. That said, not far from the Southern Cross is what they call the False Cross, which has the same sort of shape, but it's much, much bigger, and the stars are not quite as bright. Not far from the Cross, we've got a pair of stars known as the Two Pointers, because if you draw an imaginary line between them and extend that line outwards, that line will point at the Southern Cross. One of those stars, Alpha Centauri, is the third brightest star in the night sky, and the other one, Beta Centauri, is the 12th brightest. So we've got a lot of bright stars down in the south there. Above the Southern Cross, we've got three constellations. It used to be one constellation before it got split up. It used to be called Argo Navis, the ship of the Argonauts from ancient Greek mythology, but it got split up into three. Actually, it got split up into four, but the three main ones are called Vela, constellation Vela, which means the sails. You've got Carina, which is the hull and the keel, and Puppis, which is the poop deck. And just beyond Puppis, if we keep going along the Milky Way, we've got the constellation Canis Major, which means the greater dog or the large dog. That constellation contains the star Sirius, which is the brightest star in the night sky, Canis Major. And there's a Canis Minor as well, the small dog or the lesser dog, a little way away. And it has the bright star Procyon, which is the ninth brightest star in the night sky. So lots of bright stars to see at this time of year. We keep going beyond Puppis and Procyon and Canis Major and everything like that. Up to the north, we eventually get to Orion the Hunter. We've spoken about Orion many times on the program, so I won't go into detail about it, but Orion has the eighth brightest star in the sky, which is Rigel, and Betelgeuse. Just to the right of Orion, you've got the constellation Gemini. And by the way, when I say just to the right, that's looking from the southern hemisphere northwards. If you're in the northern hemisphere looking southwards, it's going to be just to the left of Orion is Gemini. Below Orion, you've got Taurus, and with Taurus, you can see a little cluster of stars called the Pleiades or the Seven Sisters. And again, we've spoken about this little cluster a number of times on the show. To the naked eye, it might just seem like a fuzzy little patch of light if you look at it. So the trick is to sort of don't look directly at it. Use what's called averted vision. Sort of look out of the corner of your eye. Don't look directly at the little cluster. Look just to the side and sort of concentrate on what you can see out of the corner of your eye. It's called averted vision. So if you do that, you should be able to see 5 or 6 individual stars in that little cluster. On either side of the Milky Way, we're leaving the Milky Way now, the sky seems a lot darker and more bare at the moment. You've got fewer bright stars, and you've got larger, sparser sort of constellations. This is because we're now looking up out of the disk of our galaxy, out into sort of deep space, and there are fewer stars between us and deep space. When we're looking through into the disk of the galaxy, we see a lot more stars, of course. But even though some of those areas are sparse and large and don't have many bright stars, if you've got a telescope or someone you know does, and you have a sort of a sweep around those areas, there are plenty of good things to see, because a good dose of magnification with a telescope can reveal all sorts of deep sky goodies that are too faint for the naked eye, like galaxies. You've got lots of nebulae of various kinds and lots of star clusters also of various kinds. So moving on to the planets, let's go to the planets now. As far as the planets go, most of the action at the moment this month is happening in the morning sky, just before sunrise, so you've got to be a bit of an early riser. So low down on the eastern horizon, we'll find Jupiter and Saturn and Venus, and in the second half of the month we'll have Mercury as well. Each one is fairly easy to identify based on its brightness, okay? So Venus is the brightest, then you've got Jupiter as the next brightest, then Saturn a little bit dimmer, and Mercury is quite dim, but it's tiny and pinpoint and quite intense with its light. But all of these planets are going to be down in the sort of dawn glow, okay? Dawn glow. So you do need to take that into account when you're looking for them. They're not going to be up high in the sky. They're going to be down in the orange sort of pre-dawn glow. And Mercury particularly will be the hardest of those to spot, because it's got to try and sort of stand out from the background, if you like. If you have a look out to the east just before dawn, you will see the Moon and Jupiter and Saturn and Venus all really close together. Okay, that should be a pretty specky sight. As the month goes on, Venus is going to be dropping down lower and lower and lower towards the horizon, and eventually it's going to become lost in the pre-dawn glare as its orbit takes it around to the other side of the sun from us. And in March, it's going to reach a position of what's called superior conjunction. This is the fancy name, which basically means it's directly in the opposite side of the sun from us, so we can't see it. And it's going to be therefore out of view, and in fact, it'll be out of view for a fair while. So we're going to lose it towards the end of February. It's going to be out of view in March and April, and it's not going to reappear in our skies till about May, when it will pop up above the western horizon this time in the evening sky after sunset. And then it's going to climb higher and higher in the sky as the months go past. It's going to be there in the western sky all the way through till December, actually. So it'll be this big, bright, star-looking thing pretty much all the year. That's going to be something good to look forward to. And the only other naked eye brightest planet I haven't mentioned yet is Mars, which you can see in the northwest after sunset. Okay, so after the sun's gone down in the west, look into the northwest and you'll see a reddish-looking star or an orangey-looking star. That'll be the planet Mars. And right at the end of February, right in the last days of February, you'll see it starting to creep up towards this star cluster I was talking about, the Pleiades, right? And in the first week of March, it's going to just sort of go slowly past Pleiades. So it'll look nice and pretty to the naked eye, but if you've got a pair of binoculars, have a look at Mars and the Pleiades together. It'll be really specky because the Pleiades stars are beautiful, bright, whitish, bluish, sparkly little gems, and then you've got this sort of orangey red glow of Mars as well. So it should be a really pretty sight, Stuart. And that's the sky for February.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. And don't forget, if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. Subscribing's easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.